Okay, 1.8. This is the last section that we are going to cover that has a lesson before we take our first quiz, which will be a group quiz. So 1.9 is just kind of more practice problems. So we're just going to work on an AP classroom assignment to cover more practice for 1.9. It's not a new lesson. So this is it. This is called the Squeeze Theorem. And in calculus, anytime a theorem has its own name, that means it's very important and you're going to need it memorized, okay? So let's go over what it is, do a couple examples of how you might see it come about. So this is the squeeze theorem. It says if f is less than or equal to g, which is less than or equal to h, when x is near a, except possibly at a, and the limit of f of x as x approaches a equals the limit of h of x as x approaches a, which equals L, then it must be true, our conclusion is it must be true that the limit of g of x as x approaches a also equals L. And that's because what we said is that near a, g is always between f and h, and if f and h are approaching the same value, then they must squeeze g in between them at a, and it must also approach L. All right, so I'll give you a general idea about how it works in our first example, and then we'll do kind of a practice AP style problem with it. So this will be a short and sweet lesson. All right, so this one wants us to show that the limit of x squared times sine 1 over x is 0 as x approaches 0. So it might be tempting just to plug in 0. If we tried a direct substitution, we would get 0 times sine 1 over 0. We can't evaluate sine of 1 over 0. That's an issue. This is actually an indeterminate form. All right. So what we want to do is try and use the squeeze theorem here. So we have to establish two other functions that have this relationship with our function. The function we're talking about is the middle function. That's the x squared times sine x. So now we need to try and establish some outer functions that will always have that relationship to x squared sine x. One's always bigger and the other's always smaller. And so when trig functions like this are involved, it's pretty straightforward to do, because if you remember, sine has an amplitude of 1, meaning the biggest it ever gets is 1, and the lowest it ever gets is -1, and then it just keeps repeating that oscillation, right? So the biggest sine will ever be is 1. So at its largest, sine will be 1, and then I would have 1 times whatever x squared is. And so that's what I'm going to choose my h of x to be, x squared times 1, which is just x squared. Because at its largest, sine is 1, and then this g function equals 1 times x squared. But any other time, sine is going to be in between negative and positive 1. So let's think of some values it could be. It could be like 0.5, in which case I have 0.5 times x squared, which is definitely less than x squared. It's half of it, right? All right, and we're going to kind of use that same logic for the other side, for figuring out f. At its lowest, sine is -1, in which case I would have whatever x squared is times -1. So that's what I'm going to let f be. F of x is going to be -x squared. And so now I have this relationship, so I'm going to go, okay, I know that it's true that x squared is always less than or equal to x squared times sine 1 over x, which is always less than or equal to positive x squared. And sorry, on my previous slide, I think I was saying just sine x. I meant sine 1 over x. That doesn't change anything, right? The largest the output of sine will ever get is positive 1, and the lowest it'll ever get is -1. All right, so I have established this relationship, and this is actually true for all x that are real numbers. All right, and so now what I want to do is take the limit of everything as x goes to 0. So of all parts of that inequality. That's going to give me the limit as x goes to 0 of negative x squared has to be less than or equal to the limit as x goes to 0 of x squared times sine 1 over x. That's the one I'm trying to figure out, which is less than or equal to the limit as x goes to 0 of x squared. All right, so I'm going to leave the one I'm trying to figure out alone. And let's just look at these outside two. Well, here I can just make a direct substitution, plug in 0 for x, and I get 0. On that side, I can also make the direct substitution as well, plug in 0 for x, and I get 0. Well, so what I've come up with is that the limit of x squared times sine 1 over x as x approaches 0 has to be somewhere between 0 and 0. So not a lot of room there, right? So therefore, it has to be 0. And I'll just make a concluding statement. So I'll say, therefore, that's a shorthand symbol for therefore. The limit of x squared times sine 1 over x as x approaches 0 equals 0, and we'll just state the theorem by the Squeeze theorem. And you do have to make that statement. That's part of justifying your answer. And you can put a little, whenever you use a justification to prove something, you put a little note to show that the proof is over. So sometimes you'll just see a shaded box, or if you're real pretentious, you can use QED. Or sometimes you'll see textbooks use a little literary dagger. Any one of those is acceptable. All right, let's do another one. So now g and h are functions defined by g is sine times the sine of the quantity pi over 2 times the quantity x plus 2 plus 3, and h is negative 1/4 x cubed minus 3 halves x squared minus 9/4 x plus 3. So f is a function such that f is always between g and h as long as x is between negative 2 and 0. And they want to know what's the limit of f of x as x approaches negative 1. Well, notice negative 1 is on that interval. It is between negative 2 and 0. And so we know that g and h surround f on that interval. So what I want to do then is look at, well, what's the limit as x approaches negative 1 of g? It has to be less than or equal to the limit as x approaches negative 1 of f, which must be less than or equal to the limit as x approaches negative 1 of h. Now I'm going to leave the 1 in the middle alone because that's what I'm trying to figure out. What I'm hoping is that the values on the outside are the same, because then I can just apply the Squeeze theorem and I will know what that middle limit is. So let's start with g. If I plug in negative 1 there, do a direct substitution, I'm going to get sine of pi over 2 times the quantity negative 1 plus 2 plus 3. All right, so that's sine of pi over 2 plus 3. Sine of pi over 2 is 1, right? Hold on, need to make my unit circle. Pi over 2 is right here. That's the coordinate 0, 1. Sine's the y coordinate. Yes, sine of pi over 2 is 1. So what I end up with is 1 plus 4. Sorry, 1 plus 3, which is 4. Okay, let's move to the other one. So for h, if I do a direct substitution, I get negative 1/4 times negative 1 cubed minus 3 halves times negative 1 squared minus 9/4 times -1 plus 3. All right. So what is that? That's going to be positive 1/4 minus 3/2 plus 9/4 plus 3. So that's 1/4 minus 6/4 plus 9/4 plus 3. All right, well that's 4/4 plus 3. So that's 4. All right, so what I've come up with then is that my limit must be between 4 and 4. And so then we'll just make our final statement, right? So therefore, limit as x approaches -1 of f of x equals 4 by the squeeze theorem. All right. Oh, put my little box to indicate I'm done with my proof. All right. That's it. I'm going to give you a student example. Give this a shot and we'll discuss it in class. Pretty similar to the one I just did. Pause it here. Try it. Come up with a value. Make sure you're practicing the justification. Right? So citing the theorem when you use it. And again, I'll see you in class.